Elements of Jacobian matrix. We have derived elements of Jacobian matrix. There are 6 submatrices: J1, J2, J3, J4, J5, J6, which take the order of these are the submatrices which we have discussed in our last class. Apart from this, we have also seen that the order is this was the order of Jacobian matrix in Newton-Raphson rectangular method. So now, in this class, today's class, we will discuss the remaining 2 methods. The first one is the Newton-Raphson decoupled method, commonly referred as DLF method, decoupled load flow studies. It is primarily based on Newton-Raphson polar method, where so Newton-Raphson decoupled method is primarily dependent on Newton-Raphson polar method. In this one, there are certain approximations which are considered. Yesterday we were sorry for the inconvenience there. So there are certain approximations that are carried out in Newton-Raphson decoupled method. So let us see what are the approximations and how these are being activated in their Newton-Raphson decoupled. Now, first of all, before going into the approximations, let's have a small recap of power systems, where actual power is a function of this basic approximated formula of active power flowing in a transmission line, and these two are the approximated power flows in the transmission line. Now, if you carefully see, normally delta value is very, very small. So at low values, you know that sin delta can be treated as approximately equal to delta, whereas cos delta is treated as approximately treated as 1. So if I employ these relations here, you know that T is a function of V and delta, and also Q is a function of V and delta. Both are functions of V and delta. But if you carefully see, in reactive power, you are having cos delta, but since delta is having very small values, Q is primarily dependent on V. Q has strong dependency on V, whereas it has weak dependency on delta. On the other hand, if you carefully see, P is dependent on V and delta. Any changes in V or delta are going to impact your P value. Any changes in voltage or any changes in angle will directly impact your changes in power. Now, carefully, if you observe in a power system, the voltage, let us suppose it is 1 at an angle of 1 degree. Normally, because of some change, let us suppose it becomes 1.02 at an angle of 2 degrees. See, what is the percentage change in this magnitude of voltage? 1 to 1.0. It is just only 2%. See, what is the change in the angle? It is 100% change in angle. Since the value is very, very small, I can directly employ here P is approximately equal to V1, V2 into delta by x at low values of delta. Now, if you see the percentage changes, V is having the voltage having very least change in percentages when compared to delta. Here in this case, cos delta is going to be treated as 1. So that's why Q is assumed to be primarily dependent on V. But whereas in this case, even though P is dependent on V and delta, we consider that P is strongly dependent on delta and weakly dependent on not. Now, keeping these things in a table now, both P and Q, they are dependent on delta and mod, isn't it? P and delta is strong, whereas with respect to the voltage, it is weak. Whereas in case of Q, this is weak, sorry. This is weak and this is strong. If we consider this approximation, now let's look back at our Jacobian map. We will neglect the weaker linkages. Now I'm going to erase this one. Now, neglecting the weak links, that is dou P by dou V is approximately equal to 0, and dou Q by dou delta is also approximately equal to 0. Which means that I am trying to neglect the weaker, because I am feeling that active power primarily dependent on delta. So I feel that it is not that much variable with respect to modeling, because I feel that it is a weaker linkage. So I am considering this derivative as 0. Similarly, in the case of reactive. Now, if I include these things here, half of my elements are 1. You see this half of the elements, the matrices J2 and J3, they vanish. So this gives me, just by considering one simple approximation, my computations have reduced to half. Now, if I separate this one, instead of complex equations, this is my instead of complex equations, see, I have got very simple linear equations. Now, if I want to change, we want to know what are the changes in delta, what I can do. See, these are the approximations which I do have in case of Newton-Raphson decoupled. If I consider this as H, M, J, and L, as already I have been mentioning for you, these four submatrices are represented as J1, J2, J3, J4, or in some textbooks, these are represented as H, M, J, and L. Now, two submatrices J2 and J3, or what we call it as N and L, both have 1. Now, you do have to do computations for only H and L. So, if I write it in this format, delta P is equal to H into, in most of the textbooks, you find in this form. What is this one? L. These are the network equations for Newton-Raphson decoupled method. Are you understood us? Now, let's have a quick look. Now, let's see if we can simplify these elements any further. Now, this is H matrix, or what we call it as J1 matrix, which is of the type of dou P by dou delta, and which has two types of elements, dou Pi by dou delta I. The other one is, this is HII. I'll represent it as, this is also part of H matrix. I'll represent it as Hij. Can anybody remember what are the equations for these two, which we have derived in our Newton-Raphson polar method? Can anybody? Anybody remembering, guys?
Qi minus Vi square.
Y minus Vi square.
Minus Qi square.
Minus Qi minus Vi square.
By II sin theta II.
Very good. This is the expression for us.
Sir.
What about this one, guys? I think this is also minus something, right? Can anybody?
Yes, so minus Vi minus Vj.
Was it sin or cos?
Sin, sir.
Right. Guys, what is Yi sin theta I? Can it be written as? You know that Yii is equal to Gii minus J Bii. Isn't it? This is YII cos theta I. This is YII sin theta I. So I am directly representing this one as VII. Or if you want to keep the same formula, you can go to that one. Now, the next one is J4 matrix, which is nothing but your L matrix, which takes the form of dou Q by dou, which takes the format of dou Q by dou modulo. Isn't it? So can somebody please LII? Anybody remember?
QI minus VI square YII sin theta II.
QI minus VI square YII sin theta I. So this is so the other one is LIJ. This is somebody okay?
Minus VI VJ
YIJ
sin
plus
sir.
so these are the expressions for Jacobian elements. Very simple things. If you observe, HII is equal to minus QI minus VI square VI. LII is equal to plus QI, just only a sign. Whereas HIJ, if you see HIJ and LIJ both are same. Earlier, I used to have lots of equations to solve in Newton-Raphson polar and rectangular method. But now, my number of calculations has reduced a lot. Just I need to determine only 3 sets of elements. In Newton-Raphson polar method, I used to determine 8 sets of elements for 4 submatrices. In Newton-Raphson rectangular method, it was 6 submatrices. Now it has reduced to only 2 submatrices. So, what are the advantages which are offered by the Newton-Raphson decoupled method? I hope you have understood what are the approximations and how the number of computations has decreased in Newton-Raphson decoupled method. Now we will have a look at the advantage. What are the advantages which are being offered by this method? First thing is time, memory. Memory required has decreased because You see the total number of iterations, the total number of equations which are required, it may remain the same, but those complex things are reduced to very simple things. So which means that you need to calculate very fewer elements. So memory requirement is reduced. At the same time taken for each iteration it is also reduced. So my time and memory both are reduced a lot, considerably. The next one is, earlier we used to have quadratic conversions, we used to have very complex equations. Now these are reduced to simple arithmetic equations. These are simple arithmetic, simple geometry. So these are the advantages which are offered by Newton-Raphson decoupled. Then what is the disadvantage? So then why don't we employ this? As already been said, Newton-Raphson polar method, however big the problem is, it takes only maximum number of 5 iterations to solve the entire problem in Newton-Raphson polar method. That is the biggest advantage. Even though it is very complex, even though the Jacobian matrix computation is very larger, the biggest advantage offered by Newton-Raphson polar method is we can get the solution at the max of 5 iterations. But here, since we have gone for the few approximations, the number of iterations required for conversion may This is the only disadvantage which is with this Newton-Raphson decoupled method. Device. Have you understood Newton-Raphson decoupled method? How many of you have understood Newton-Raphson decoupled method? If I ask you for a short answer, what are the approximations which are considered in decoupled method and devise the elements for Jacobian matrix in Newton-Raphson decoupled? Can you write it down? How many of you are okay with this one? Can you please raise your hands so that I can proceed to the next one? So moving on to the next one, the last method of this unit number 1. It is a fast decoupled method where we do employ few more approximations. Newton-Raphson fast decoupled flow method. This is the last method in your unit number 1. It considers few more approximations to the Newton-Raphson decoupled method. So first of all, let me write what are the approximations which are considered. The approximations which are considered for Newton-Raphson fast decoupled method are the delta values, which are the angles of bus voltages. They are very small compared to the angles of admittance. They are very small compared to the angles of admittance. So keeping this in view, what I can say is delta ij is far less when compared to theta ij. Delta ij is far less when compared to theta ij. So I will take as cos delta ij approximately equal to 1. I have already mentioned cos delta ij, I have taken it as 1. And I'll consider sin delta ij is approximately equal to 0. Sin delta ij is approximately equal to 0. And also, try to remember this one. We will come across this particular one. Next step. Dij, sin delta. Since sin delta value is very, very low, this particular term, it is considered to be very, very small when compared to the remaining terms. This is the first approximation. And the second approximation is reactive power induction are considered to be very small. So, if you see these two equations, here there are two terms. So, I am going with an approximation that Qi will be very less when compared to mod Vi square Vi. So, this is the approximation which I am taking up here. To minimize the computation in this one, and this one is for this one. Okay. So, now we will see how these two approximations will affect these two equations. Okay. Now, on seeing this one, these two are the approximations. We'll go with this one approximation. If we consider this approximation, what is the change in HII and LII? Qi becomes neglected because Qi is considered very smaller when compared to this one. Both Qi get neglected. So what will you be getting? Considering approximation 2, what will you be getting? HII is equal to LII, that is equal to mod Vi square Vi. Mod Vi square Vi. Assumptions. Now considering the first approximation. Considering the first approximation, let me consider this particular term. I will expand this one. Hij is equal to Lij, that is equal to mod Vi, mod Vj, Yij. Now this one is sin of theta theta ij. Can I write it as delta ij? Delta j minus delta I is delta ij. Now I am expanding this term. Sin a plus b, which is plus now you see this is the term. Just I have tried to expand it. Isn't it? If we consider, I think there was a minus. Now if you see sin theta ij can be approximately considered as 0. No problem. The other one is cos delta ij. That is cos delta ij. This is somewhere considered to be 1. This is considered as approximately 0. So now what I am getting here? This will be considered as 1. Isn't it? So if I consider this one as 1, so what is the remaining term? I will consider this one as negligible. So the remaining term is yij into sin theta ij. This is what I have written here. Is equal to yij sin theta ij is bij. So this is my expression for hij and lij. See, my calculations are further reduced. If I compute hij, then I can easily go with li. If I go with hij, I can easily have li. What is it, guys? Now, hoping that you have understood these things. I am writing them in matrix format now. H matrix is this one. If it is I, this is minus vi square bi. If it is hij, vi bj bi. And I am trying to write it as so
Yeah, guys, I hope you are able to see this one. This is regarding fast decoupled load flow method. These are the approximations. See the approximations and the derivations of these elements. And the procedure which we are supposed to follow for Newton-Raphson decoupled method. So for this is for decoupled Newton method. We started with active powers, reactive power. We have seen what are the weak couplings and what are the strong couplings. We have tabulated them. And next is we have neglected the weak couplings. Written this in the matrix formats. This is the matrix format. And we have derived the expressions for these things. And the advantages and disadvantages and the approach for the better convergence. You can go through this one. And after completing this one, you come back to the fast decoupled method. In the fast decoupled method, you note down what are the approximations, approximation number 1 and approximation number 2. And after that, you try to employ these two approximations and determine the final expressions of Hij, Lij, Hii, and Lii. And you mention them in the matrix formats. So these are the matrix formats. Guys, there is a small mistake here. This is delta mod V. Try to change here. And this is the procedure. I hope you have understood this decoupled and fast decoupled methods. Very simple, just a few approximations will reduce the time taken for each iteration.